Hey students, I was just asked to make a video about chapter 29, number 59, so let's give it a try. I have the problem here in the hard copy. I didn't bother to print it this time, but it says, consider an electron orbiting a proton, so this is a hydrogen atom, and maintaining a fixed circular path, and they give us the radius, by the Coulomb force. Treat the orbiting particle as a current loop and calculating the resulting torque in the system when the magnetic field of 0.4 Tesla is directed, and there it is, perpendicular to the magnetic moment. The magnetic moment of this electron. Okay, so writing the idea of torque, which is the magnetic moment across the magnetic field, if I were to look at a proton here and take an electron, and I'll just say the electron is orbiting in a counterclockwise direction, that would be the equivalent of a positive going in the clockwise direction, so the current is going in a positive direction. And then using a right-hand rule, number 2 here, I can put my right hand and look at the fingers as the motion of the current, and so my thumb is in, so I'll put a little X here, meaning in for the magnetic moment. So if I set up a magnetic field that is perpendicular to that, I would calculate the magnitude of the torque as mu times b times the sine of 90 degrees. And I think we just need to keep going with this equation, but as long as I'm here, I'll do my vector cross product, and so putting my fingers in the direction of mu and rotating my wrist so that I can close my hand, you'll see my thumb is pointing downward. And so if this little disc here was this speaker here, I would have a orbiting electron this way, which means current this way, which means magnetic moment in to the paper. And so mu cross b gives me my thumb pointing down, and that's going to rotate it around like this. And I guess because of momentum, it would rotate around and be happy right there, but it would go past and then oscillate back and forth. And so the magnetic moment wants to line up with the magnetic field. And so right now, they're 90 degrees, and that's why we get the maximum torque. And so the challenging part of this problem really is right there. Because we know the magnetic field, they tell us it's 90 degrees, but the magnitude of the magnetic moment is the number of loops times the current times the area. And the number of loops is just 1, so I'll just drop that. But this is where it might be a little more challenging here, is what is the current? So the current is the rate at which charge flows with time. I'll call it a delta Q over delta T. And so if you watch this electron go around one time, the amount of charge that would go by would be just E, the charge of one electron, and I'll call capital T the time, or what we call the period, of one revolution. And to study this a little further, I'll do Coulomb's law, because Coulomb's constant times the two charges, and one's a proton and one is an electron, so they each have a value of E over R squared. That's the force between them. And if I multiply, or if I set that equal to, so I guess this is back to chapter 23, and this is all the way back to chapter 6, so Physics 121. This then is the connection that you can see is going to give me V. And so V would be Coulomb's constant, E squared. I'll put the m and r. Let's see, r, put the m. That would be v squared, and so that should be the square root. And so that's how fast it is going. Now, to keep moving along here, if I took the velocity and multiplied by 1 period, that's 1 revolution, it would go the circumference, which is 2 pi r. So, in other words, the period would be 2 pi r divided by the velocity. And I can use that up here. So this will be E, and this will be then a 2 pi r and times a v. And remember, v is the square root of Coulomb's constant, E squared m r. So that's the current. Now, let me also continue on by saying the magnetic moment is this current. So let me maybe simplify this a little bit. I'm going to just take the square root and leave the k, the m, and the r alone for just a second. But the square root of e squared is just an e, so that makes a e squared on the outside divided by 2 pi r. So that's what I have for the current, because the area is pi r squared. And that means a pi will cancel, and even one of the r's. And so I should have then, let's see, an e squared over 2, and a square root of k, m, and r. And I'm going to do something also kind of interesting. Why don't I take this r and put it inside of the square root? So this becomes an r squared. Because if I do that, then one of those r's cancel off. And I end up with e squared over 2 times the square root of k r over m. And that's probably why this problem has the magenta color, is all of this work, particularly right here where I got to go back to chapter 23 and back to chapter 6, put it together with the definition of current, which is chapter 27, then put it together with chapter 29. So we've got 4 different chapters we've got to put together. Now, I did a lot of math here, and I really am questioning this. But I kind of like what I got. Let me just check my units before I go and punch this number in here. Let me go to a page 2. But it's always a good idea maybe to do some unit analysis. So here, unit analysis, the charge is going to be Coulomb squared. And inside here is going to be Coulomb's constant. There's a lot of units there. Coulomb's constant was a Newton times a meter squared over a Coulomb's squared. Okay. Then we have the radius, which is in meters. And then we have the mass, which is in kilograms. And again, let's just look a little careful at this. And maybe it's worth pausing. Yeah, actually, I think that is going to work, because let's look at what units I expect to get for the magnetic moment. It should be units of current, so that's an amp, times units of area, and that is meters squared. So looking a little more careful at this, I will see that, especially down here, taking the square root of coulombs squared gives me coulombs on the outside, and then that will cancel with 1. So those will go away. And inside of this square root, I have a Newton, which a Newton is a kilogram meter over second squared. And also then including this meter cubed from these together, and kilogram, oh good, I like where this is going. Kilogram's gonna go away. And then looking at this numerator, this is meters to the 4th power, but I'm taking the square root, so that gets meters squared. And then taking the square root of second squared gives me a second, so I'm going to have a coulomb over a second, which is an amp. And yeah, sure enough, that does come out to be the right unit. So that's a good indication that I'm on the right path here. All right, so this is my magnetic moment. And for torque then, to finish this, torque, I have to take this magnetic moment, E squared over 2 times the square root of Coulomb constant R over M. Okay, so there's the magnetic moment. And then I have to multiply by the magnetic field. And so let me put in my numbers as well as my units, but let's work on the numbers here. I'll do this inside here first. So let's go 9 times 10 to the 9th for Coulomb's constant. Radius, what'd they say? 5.29 times 10 to the negative 11. And the mass of the electron, oh good, and I get to do it today, which is Halloween. Yay! And so there's my times 10 to the negative 31. And so if I just hit enter, that's all that stuff inside of the square root. So if I take the square root of all of that, that's stuff there. Since I'm just right next to the B, let me just double check. Yeah, B is 0.4. And then over here, I will go times 1.602 times 10 to the negative 19 squared. And then divide by 2. All right, so I get 3.7 times 10 to the negative 24. And let's take again a close look at our units. Now, I already spent some time pointing out that that right there would be an amp times a meter squared. That was all this stuff up here. And then when I multiply it by a Tesla, and then I might pause and say, okay, remember what a Tesla was. A Tesla is the amount of force, Newton, you get when you have 1 coulomb moving at 1 meter per second. And of course, we could also replace this amp with a coulomb per second. So I'll do that. And that's nice because that coulomb will cancel with that coulomb. Oh, good. That second with that second. And that meter with that meter, and I'm left with Newton meters. Good. And that is the correct unit for a torque, a Newton meter. All right. Hope that worked well for you. All right. Take care.